So folks, now we want to look at actually utilizing that double integral formula that we looked at in the last video. That is, we could think of this double integral as being the integral from some theta equals alpha to theta equals beta, from some r equals a to some r equals b, of some f of r comma theta. And then the key part to keep in mind here is that the last part of that, what was the dA in our expression of the double integral, is to express that as r dr d theta. And again, you should be curious about where that factor of r comes from, and we'll see that in our in-class work, but that actually is going to be an important thread through the remainder of this chapter. So we're going to go ahead and evaluate this integral here. You can click here to look at a visualization of this, but essentially what we have is we've got an annulus, and then living above this annulus we've got a particular surface, and in order to be able to evaluate this integral, well, there's probably other ways, but remember the double angle identity. If you have trouble remember this, I remember the sum of two angle identities for sine. And so from there you can quickly derive this particular double angle identity, and we'll be using a version of that in this problem. So here we go. I think before you go too far in these problems, it's always essential that you draw yourself a picture of the region that you're working with. So here you can see we've got, again, an annulus. We can think of this as a circle with or the region is circular, with the lower radius being 2 and the upper radius being 4. Be careful as always with those squares. There's no other stipulations on this region, so I think that's our region R right here, this shaded annulus right here. So let's go ahead and convert this first of all to polar integrals. So we're going to use the substitution just like we used a lot of times in our polar substitutions. We're going to use a substitution that x is equal to r times the cosine of theta, and that y is equal to r times the sine of theta. And so then we could say that the double integral of r over r of xy plus 10 dA we can convert into polar coordinates as the integral from, we'll address that in just a second, of r cosine theta times r sine theta plus 10 r dr d theta. It's customary, although not absolutely necessary, but usually given all other things we try to integrate first with respect to r and then with respect to theta, although you could adjust this if the situation warranted it. So our radius here, we see our radius is going to go from 2 to 4. That's reflected in this region that the radial changes in the radius run over that interval. And then our theta, we want the entire, so, you know, for a given radius, one way to think about this is, let's see if we can zoom in on that a little bit. Like, let's say we were dealing with this radius right here, and what we want to do is we would want to sweep our integral around the entire circle. And so we would do that from r equals 0 to from theta equals 0 to theta equals 2 pi. Theta equals 0 to theta equals 2 pi. Okay, so now, I mean, as far as the new calculus is concerned, we're done with the problem. It's just simply evaluating this. So let's see here, we've got the integral from theta equals 0 to theta equals 2 pi times of the integral. So this iterated integral here, r equals 2 to r equals 4. And then, let's see here, we could rewrite this as r squared cosine theta sine theta plus 10 sitting inside there, and then times another factor of r and dr d theta. What I'd like to do though is let's go ahead and apply this identity that I mentioned before. So another version of this identity says, well, if I divide both sides by 2, I'd have 1/2 the sine of 2 theta is equal to the sine of theta cos of theta. And so I'm going to replace my sine theta cos theta right here with the 1/2 sine 2 theta. So let's go ahead and do that. So that gives us 1/2 r squared sine 2 theta plus 10 r dr d theta. If we go ahead and distribute that r through, quickly running out of room. gives us 1/2 r cubed sine 2 theta plus 10r dr d theta. So now integrating with respect to r will give us the integral from theta equals 0 to theta equals 2 pi of, let's see here, this would give us 1/8 r to the 4th sine of 2 theta plus 5r squared, evaluated from r equals 2 to r equals 4 times d theta. And so we just get the evaluation of this inner integral to do. So let's see here, that'd be the integral from theta equals 0 to theta equals 2 pi. And then inside of here we'd have 1/8 r to, or 4 to the 4th times 4 to the 4th sine of 2 theta plus 5 times 4 squared minus, and then we'd have 1/8 times 2 to the 4th sine 2 theta plus 5 times 2 squared d theta. And so what do we see here? Well, 4 to the 4th is a large number, but then I think it's 256. We divide 256 by 8, that brings us down to 32. But then we'd have another, this is 16 divided by 8 is 2, so that would give us a 30. Cosine of 2 theta, or 30 sine of 2 theta. And then let's see here, we'd have 16 times 5 is 80, and we would subtract from that 5 times 4, which is 20, so that gives us a 60. 80 minus 20 is 60, so that gives us a plus 60 d theta. Now we're ready to evaluate this integral with respect to theta. So let's see here. We certainly want a minus cosine 2 theta. So when we take the derivative, we get 30. So it makes a 15 there. So minus 15 cosine 2 theta plus 60 theta, evaluated from theta equals 0 to theta equals 2 pi. Folks, I've run out of room here. Let's see, if we plug in 2 pi for the cosine, that's 4 pi inside of the cosine. The cosine of 4 pi is 1, so that's a minus 15. And if we plug in 0, we would do, so those two would cancel. When we plug in 0, we would also get a minus 15, so we're subtracting that from the first. And so we're really just left with 120 pi there. Okay. So there's a brief example of doing one of these polar integrals, and I highly encourage you to click the link to see the visualization of this, and I hope this video was helpful.